Hi, I'm Darren and welcome to Level Up EE Lab. I finished the construction and the testing of all three of my active probes, and I have a lot of material to cover today. So let's get right to it. Let's begin this episode with my choices for the probe construction. For comparison, here's my version of Mr. Carlson's Super Probe. It's 35 millimeters in diameter and about 150 millimeters long across the end caps, so it is fairly large. Another example is this classic Heathkit probe. It's quite a bit smaller at 22 millimeters in diameter and around 125 millimeters from cap to cap. I'm going to challenge myself to build these quite a bit smaller. How about using half-inch brass tubing? That's only about 13 millimeters in diameter. The three probe circuits are very simple. They're less than a third of the number of components in the Super Probe, so it should be possible to stuff the electronics inside this volume. And as it turned out, it was very doable using all SMT components. Here's the Bob Pease probe, the most complicated circuit of the three, fitting nicely on an 11mm by 75mm board. It's mostly single-sided, but I did have to route a few traces on the backside, along with the ground plane and a surface mount area for a coax connection. One of the hallmarks of the Bob Pease design is its low input capacitance. Bob built his in free space using leaded components, but I had no choice but to use surface mount FETs for my version. I did remove the ground plane under the spot where the probe tip will solder to the board. Now that will avoid adding a few puffs at that connection, but still, my design likely will have a bit more input capacitance than Bob's. The other two are simpler. Here's Steve Hageman's design, the one that uses an op-amp, the OPA814, which comes in a SOT23 package, along with the dual diode array. Everything's on the top side except for R4. Now that's the inverting input feedback resistor, and by best practice you want to minimize that loop length. The pinouts of the OPA814 pretty much force you to put that on the backside and connect it with a couple of vias, so that's what I did. And here's my version of David Jewsbury's design. It's going to use one of the dual gate BF998 FETs that I reluctantly bought off of eBay. His design uses a gimmick input capacitor made from the PC board copper foil. You can see it here at the front end. I'll solder the probe tip to this pad, which is then capacitively coupled to this pad on the other side by the FR4 thickness. By design, this should be about a half a puff. Okay, now that I've got the three board layouts, I can design the rest of the probe structure. And here's what I came up with. Like I said, I designed it to fit inside half-inch brass tubing, which on the stock that I have here measures 12.05 millimeters inside diameter. And just like I did with my Mr. Carlson probe, I designed custom end caps that I'll 3D print. The back end cap has two apertures. The smaller one will accommodate RG174 or 316 coax for the output signal, and the larger one will let in up to 3 conductors for power and ground. It's held to the tube by using number 3 screws that engage nuts pressed into blind pockets. This is one of my favorite techniques to secure 3D printed plastic parts. It works much better than trying to thread into the resin itself. The front end cap, of course, has the probe tip protruding from it. For that, I'll use 0.8mm diameter brass rod. To make the ground connection, I've got a 5mm length of 1/8" brass tubing concentric with it. I'll solder a short piece of wire from it to the ground plane on the PC board, and then fab up some ground contact springs to fit over the tubing, much like on a scope probe. The PC board assembly is loosely held by 2 slots in the end caps. And lastly, to protect the delicate probe tip when not in use, I've designed bayonet mount caps that twist and lock under the front end caps. Okay, I'm at a good break point here on the fabrication of the various bits and pieces. I've got the 3D printed parts all printed, and I did go through several iterations of the end caps to get the designs that would work. And kind of, I guess the trickiest part was getting this a protective cap to snap into place. This always takes a little bit of finesse in plastic design because you're relying on plastic to deflect and click and all that, but it's working fine. So I think this is going to protect the end of the probe from being damaged when I'm not using them. So of course each probe has an end cap for the back end for the wires to come out, a front end cap for the probe tip, and then of course the twist and lock cap on the front. I have to cut the probe bodies to length. That'll be next, and then drill out the holes for the screws to fit through. And you can see the the blind pockets here where I've got the nut stuffed in there, and then the screws cut to length. Now these are number 3 fasteners, so they are pretty small, and it's only, I think, about 4 millimeters long is what I needed to trim those screws to. So definitely some tiny hardware. Here's the 0.8 millimeter stock I'm going to use for the probe tip. Here's the other hollow tube that I'm going to use for the ground connection. That'll be concentric with the probe tip. And then lastly, I did populate and test all 3 boards. 2 of them I ended up fabbing myself. The third one, the Bob Pease design, I did get boards made for that one, mostly because everything was really tightly packed, and the stuff on the backside was going to be tough. Really tough to get a home-built board to turn out correctly. So I waited a few weeks to get a fab board. I'm glad I did, because this is really easy to solder. And this guy right here, you can barely see it. In fact, I'll try to get it on screen here if my camera will cooperate. That's a potentiometer. I mean, that thing's only like 4 or 5 millimeters square and takes a really tiny tool to adjust. So that's the offset potentiometer. All right, so up next, I'm going to mark out the tube lengths, cut the tube, get the holes drilled, and get everything assembled. I've made really good progress on the mechanical fabrication and assembly, and I thought I'd pause here before I finish up to show some of the features of this design as it goes together. So obviously I've fabricated the 3 brass tubes. This turned out to be pretty easy to cut to length. The tricky part was drilling these holes. They had to be fairly precisely located, and as you can see, the way I designed these, they're not at the same angle from one end to the other. It's just the way that the shape of the 2 end caps worked. I needed to stagger them, so that was a bit tricky. I do have the luxury of having a mini lathe and a mini mill, which makes this kind of fab work a heck of a lot easier and a lot more repeatable. As far as finish goes, all I did was polish them with I think a Scotch-Brite, like a very fine Scotch-Brite pad. I don't think they're going to stay shiny for very long. I thought about tin plating these, but tin tends to pick up fingerprints so easily, and then you get almost permanent fingerprint marks in it, similar to like old radio chassis that's got tin or zinc plating can do that. You get that kind of oxidized fingerprint on there. So I'm just going to leave them like this for now. As far as the rest of the fab goes, I've got one of the 3 ready to close up right here. I know it's probably not going to show very well on my camera I'm using now, but I've got my older Sony camcorder that has a much better high resolution zoom, so I'm going to switch over to that, and we can take a look at the tip end. It's probably the most difficult part of the construction. If you recall, I had to make little, I think they were 5 millimeter long sleeves, concentric sleeves for the tip that then had to be soldered to a little length of wire, and that little length of wire is getting soldered to the ground plane of the board. That way I can have the ability to put a ground connection right near the tip. I'm going to set this down for a moment and show, this is I guess you could call it a prototype of the spring idea that I have. It's very much like an oscilloscope probe. Now this one doesn't fit on here with much spring retention, so I'm still working on it. So the challenge is the wire that I've got, this 0.8 millimeter brass wire, which is also making the tip, by the way. I had no idea what temper it was going to be. It turns out to be pretty soft, so trying to make a spring out of it is asking quite a bit. So we'll see what I come up with there. The rest of the construction, pretty easy. Obviously, I have to have coax coming out and power going in. The coax is just a length of RG174. And for this version, this is the dual gate FET version. I just need 2 wires going in. So this is 22 gauge stranded, very soft wire, very soft insulation, very flexible. I think that'll be best to use that for these probes. And then lastly, just using a little piece of heat shrink tubing as a strain relief to kind of keep the wires positioned as I slide the tube, over the board, push it up over the front end cap. And then this part's a little tricky because there's not that much clearance. Put the end cap in place. See if I can do this live. There we go. All right, and then I've got the 4 screws that are in the little tray here to install, and then the assembly will be complete. I just have to repeat it on the other 2. I finished the assembly of all 3 probes, and I'm very happy with how they turned out. I think this mechanical construction is very rugged. This one here on the left, this is the Bob Pease design. The one in the middle, this is the OPA 814 op amp. And this one over here on the right, this is the dual gate BF998, the dual gate FET. And all 3 of them have about 3 feet or 1 meter of wires on here. Of course, there's this signal output coax, and then whatever power requirements I need. 2 of the 3 need split power. The dual gate FET only needs single, B plus and ground, doesn't need a negative supply. So at this point, I need to measure their performance, and to do that, I came up with this little test fixture. Now let me try to get it zoomed in here on camera. It's always a little tricky to get it to focus to go, but I think it's set. That should be sharp. What I'm doing here in the center, you can see 2 resistors. There's a 50 ohm resistor from the center connector to ground, and that second resistor is just a 0 ohm jumper for now. I was going to play around at some point with additional series impedance, so I put that in there in case I needed to do that, and then some unpopulated pads just so I can solder and unsolder as many things as I want. But the most important thing to notice here are these coils on the left and the right, and what I've done here is copied a great idea that Alan showed on his channel, W2AEW, for a technique to minimize the inductive coupling from probes to a test circuit. So literally, the way this works, and I'll use my scope probe here because that's what this size is set for. You can see that when I put this in to make a measurement, that those coils make contact with the ground and make contact with the signal, and there's very little additional length there, so the inductive coupling should be very, very low. Now, this set on the other side, on the left side, fits to the actual geometry of my 3 probes here. So I'm going to use this to be able to make measurements on the probe performance. Before I start using the test fixture, I want to measure its reflection coefficient to see just how good it is to a pure 50 ohm dummy load. And the smart way to do that, of course, is to use the Nano VNA. And what I've done here, of course, I've calibrated the Nano up to 400 megahertz. That's the upper limit of what I'm interested in here for the performance of these probes. And then I have it coupled to the port 1 and just check the S11. That's the reflection coefficient parameter. And I could just zoom in on the screen here and we could look at it this way as I move the marker back and forth. But the easier way to do this is to connect the Nano VNA to the software and export and capture the information, which I've done. And I'll put it on screen now so we can take a closer look at it. The bottom line is the reflection coefficient for this fixture looks really good. It starts below minus 60 dB. It does increase with frequency. That's normal, but even at 400 megahertz, it's just under minus 30 dB, which is really good. So this fixture performance is going to be just fine for the test measurements I need to make. I can also use my Nano VNA to measure the probe performance by connecting the probe output signal to port number 2 and looking at the S21 parameter. Now this is feasible for a couple of reasons. Number one is the nano output signal on port 1 is within the sense range of all 3 probes. It's minus 10 dBm or 200 millivolts peak to peak into 50 ohms. It's not too strong that it would activate the clipping diodes in this guy. This is the OPA 814 op amp probe, and nor is it too strong to overload the input on the other 2 probes. The second factor is the output signal on all 3 probes is either 0 dB of gain, in the case of the Bob Pease probe and this guy, or it's even lower. It's minus 20 dB actually in the dual gate FET. So I'm not going to overload the capability of port number 2 here. And then I can use, of course, the S21 parameter like I mentioned to judge the probe performance over frequency and figure out its bandwidth. Now this is a much better approach than trying to use a signal generator and an oscilloscope, which was my original thought when I was just starting on this project. That's what I would do. This is automatic. It does a sweep and boom, you got your results. But more importantly, the scopes that I have, my Siglent is a 200 megahertz scope and my Tech scope goes up to 300 megahertz. Those bandwidths are within less than 400 megahertz, which is really the upper limit of what I want to measure here. So I would have had some limits on the data just because of the bandwidth limits on the scope. Doing the signal generator would have been problematic because I don't have one that does a sweep, so I'd have to do a bunch of manual steps, and that would have been arduous. So all things considered, using the Nano is much better, and like I did with the S11 parameters, I can use the software to capture the data and generate graphs. So that'll be much faster and generate much more interesting results to look at. And the last thing I would say here on the setup, I have to provide power, and I'm going to pan the camera here so we can see that. It's just my Heath 2718 power supply on the bench. That's real easy to set for split mode operation, which I've done here, +5 and -5 volts for the op amp probe, and that's what I'm going to use to power these setups. All right, here's the results of the OPA 814 op-amp probe. And as much as I'd like to video the screen of the Nano, it's just not practical. There's just no angle that you can set this little guy where you're not going to capture the lens reflection or the reflection of some light in the room. And it's just much easier to export the data using the software and make a plot. So that's what I did. So here's what that looks like. And I think it looks really good. It's mostly flat up to about 200 megahertz. There is a slight increase in response in the mid-range. Then it rolls off with a little bump just before the 3 dB point kicks in at 250 megahertz. Now, I have no idea what this cliff is here at 300 megahertz, but it's basically irrelevant. It's way past the 3 dB point by then anyway. I'm also showing the results of an LT Spice simulation that I did, and that's basically worthless. It overpredicts the bandwidth. Now, I suspect that I'm just not modeling the effects of the termination impedance and the losses in the coax correctly, among other things. I will show it on screen here for a few seconds in case you guys have some insight as to what might help to put in the simulation. But at this point, it's kind of not beneficial because I'd be altering a simulation to match the performance of something that I already know. So it's kind of backwards. But nonetheless, I did attempt to do a simulation. Another point here is this 250 megahertz bandwidth does outperform Steve Hageman's design by about 50 megahertz, and I'll show here his response curve from Steve's article. I am using the more modern OPA 814, and Steve, in his 10-year-old design, used the former and now obsoleted OPA 656. If you do a side-by-side comparison of their spec sheets, the 814 is 50 megahertz higher across the board. It's got a 50 megahertz higher gain bandwidth product, unity gain bandwidth, and large signal bandwidth. So I'm attributing this slight bump in performance to that chip and certainly nothing that I did. Switching gears now, here's what the results of the Bob Pease design looks like. Now, it doesn't disappoint. It's mostly flat up to around 50 megahertz, then it drops like a rock. It hits the 3 dB point at 83 megahertz, and that's right where Bob said the limit was. And once again, I did a simulation, and once again, it was worthless. I think it's the same problem. I'll show it on screen what the construction in LT Spice looks like. And once again, I suspect I'm just overly simplifying the load conditions, and I'm not seeing what the bandwidth roll-off would really look like at high frequencies. And time for probe number 3, the BF998 dual-gate FET. Now, as a reminder, I bought these FETs off of eBay, and I was concerned that I was going to get a box of junk. Well, as it turns out, my concern was overblown. The performance actually looks pretty good. Now, remember, by design, this probe has about a 20 dB insertion loss no matter what. So I need to look for performance here between minus 17 dB and minus 23 dB. And up to 400 megahertz, which is the same limit I'm using for the other two probes, it looks really good. It's the best performance of the three. In fact, I needed to recalibrate my Nano VNA to 1 gigahertz to determine the actual bandwidth. I'm probably pushing the limits of my setup, but nevertheless, it still gave me a believable result, and here's what that looks like. It does hit minus 17 dB at around 580 megahertz. David says his design is plus or minus 2.5 dB out to 1.5 gigahertz, which I don't doubt. There could be some nuances in my design and construction that are causing this behavior, but I am suspicious that these FETs that I got off of eBay are at a minimum knockoffs of the originals, and they might not have the same performance as the originals. But clearly they're working well enough to be on 500 megahertz, which for my projects is perfectly fine. I rarely go over 100 megahertz, let alone 500. The final set of data that I want to talk about today are the S11 parameters for all three probes, and also the same measurement made with my PP215 200 megahertz scope probe that came with my Siglent scope. That information will tell me which of these designs will load a test circuit the least. And here's what that data looks like. The orange line is for the fixture with no probes connected to it. It's the same data that I showed earlier. And above that, the purple line, that's the BF998 dual gate FET probe. So of the three probes, it has the lightest loading, which makes sense based on their designs. Next comes the Bob Pease design. It also is lightly loading the circuit, and it's not that much more than the dual gate FET, and it's consistent with Bob's assertions. And bringing up the rear is the OPA 814 op-amp probe. At frequencies above 150 megahertz, the reflection coefficient is 10 dB or more. And for reference, the dashed line is the PP215 200 MHz scope probe set to 10 times and connected to my Siglant with it set to a 1 meg input. Now Steve says in his article that the op-amp probe will present an impedance to the circuit similar to a 1 meg 15 picofarad scope probe. I looked up the specs on the PP215 and in 10 times mode it's 10 meg and 16 picofarad, so it's kind of comparable to what Steve says, but obviously it does perform slightly better. Now that I've got 3 active probes to choose from, I can return to the original problem that got me started down this path in the first place, and that is I want to look at the output signal of my HG10 VFO on a spectrum analyzer. Now if you recall, the HG10 specs say that it needs 50k ohms or more of load impedance. And here's what the output signal for the 80 meter band looks like with a 50k ohm load across the output. Now this was captured using my PP215 200 MHz probe on 10 times setting applied across that 50k load. Pretty conventional. It is a funky waveform for sure. That's why I'm curious to have a look at it in the frequency domain. But also notice that the peak-to-peak voltage is just under 10 volts. That's consistent with the HG10 specs, which are 5 volts RMS into an open circuit, so this result is believable. But that's just way too high for any of these 3 probes. I need a signal that's only a couple hundred millivolts peak-to-peak, not 10 volts. Fortunately, that's an easy problem to solve. All I need is a 2 resistor voltage divider, which I can get by modifying my probe test fixture. So what I did is swap out the 0 ohm jumper here for a 56k resistor and swapped out the 50 ohm resistor here for 2k. The overall resistance with them in series is 58k, which is fine for the HG10, and now the voltage at the common connection between them will be around 340 millivolts peak to peak, and that's what feeds into the probe input points here and here. And because all 3 probes have input impedances well above 2K, putting them in the circuit across that 2K resistor won't appreciably skew the results. Okay, with this modified fixture in place, you can see it here in the background. Here's what the 80 meter signal across that 2K resistor looks like. There's 4 plots here. The one in the upper left, the purple graph, that's the PP215 probe by itself. Now it looks very much like the signal taken across the entire load, but of course it's at a lot lower voltage, around 264 millivolts peak to peak. And that's compatible with all 3 probes, so now that I know I'm not going to blow up my probes, I proceeded to make the measurement on all 3 of them one at a time, and that's the other 3 graphs shown here in yellow. And of course the scope was set to 50 ohms input impedance for each of these 3 probes. And looking at them one at a time here, the OPA 814 is almost identical to the PP215. In fact, it's scary how close it is. It only differs by a couple of millivolts. The Bob Pease design is a bit different in shape, and it's also a bit higher in voltage, but not dramatic. And the BF998 dual gate FET has the most different appearing signal as compared to the PP215. And also notice the output voltage is considerably less. Again, that's because it has 20 dB of natural attenuation. And now for the finale. What does this signal look like in the frequency domain? Well, I now have hardware and a signal that's compatible with my TinySA, so here's the results with each probe connected one at a time to the TinySA. The frequency range was set from 1 MHz to 80 MHz, and big surprise, there's a crap ton of harmonics in that signal. The OPA 814 and Pease probe results are very close to each other. Their frequency peaks follow the exact same up and down trend, and they're mostly within a couple of dB of each other. The dual gate FET is also showing equivalently useful information, but of course its peaks are about 20 dB lower than the other 2 probes because of the probe's inherent attenuation. Now this is a broad frequency sweep at a 300 kHz resolution bandwidth, so don't slice and dice the absolute magnitude of each peak. Doing that would take several narrower frequency sweeps at a much lower resolution bandwidth, and likely would need a better instrument than my TinySA. But the big takeaway here I have from these results is that any of these 3 probes would work just fine for me. Even though I believe I could use any one of these probes for the projects that I typically work on here in my lab, I feel like I should try to do an objective ranking here before I close this episode out. So keeping in mind, you guys have seen the types of projects I do here. They're restoring vintage amateur radio gear, new amateur radio transmitters, receivers, test equipment, so on. I'm still staying within the HF spectrum, not much more than about 30 megahertz. So here's how I would rank these 3 probes. Let's look at this table now. Keeping it somewhat objective, here's how I rank these 3 probe designs. I chose David's dual gate BF998 as my first choice, and here's why. It's got the highest overall bandwidth, has the least loading on the circuit it's connected to, and it has the simplest power supply requirements. Now, it does have 20 dB of inherent loss. There's always some negative no matter what, and that does limit its overall sensitivity as compared to the other 2 designs, but I think overall it'd be my first choice. I put Steve's OPA 814 as a second choice and Bob Pease's design as a third choice using the same ranking criteria. Of course, that doesn't mean that they're unusable or that I would never use them. That's just how they happen to rank in the objective criteria that I chose here. So I hope you enjoyed this 2-part series that I did on active probes. If you do have some questions about these or some additional test measurements you'd like to see me attempt to make on these, let me know in the comments below. So until next time, bye for now.